The Rajiv Gandhi Institute for Contemporary Studies, I extend a warm welcome to you at Jawahar Bhavan. My name is Simi Sunny, and I'm a staff member at RGICS. A gentle reminder to please put mobile phones on silent mode. Let me begin by extending a special and warm welcome to Shri Rahul Gandhi, Member of Parliament, Trustee of Rajiv Gandhi Foundation, and Chair of our Advisory Committee. Mr. Gandhi will be chairing the discussion this evening. A special welcome also to the large number of students and young people present, and to many distinguished members of the Council of Ministers and members of Parliament who are here this evening. Born through the far-sighted vision of Shri Rajiv Gandhi, the core belief at RGICS is that voice and technology will shape the future. The current focus of our work is on democratizing the policy space by enhancing voice and strengthening the role and capacity of elected representatives, political activists, and common citizens in policy formulation and implementation, and on democratizing technology to find solutions to the challenges we face. Today, we start a new discussion series called The Cutting Edge. In this series, we hope to bring you public discussions on cutting-edge ideas that will shape our future. The first discussion in the Cutting Edge series is on aerial robo-swarms, based, as you will see, on a very powerful robotic technology that is already redrawing the contours of power in many realms. To talk to us about the cutting-edge robotic technology this evening, we are delighted to have with us one of the world's most distinguished and well-known robotist, Professor Vijay Kumar, Professor in the School of Engineering and Applied Sciences at the University of Pennsylvania. We'll begin with the remarks from Shri Rahul Gandhi, which will be followed by Professor Vijay Kumar's presentation. We'll then have a question and answer session. In conclusion, we'll have Professor Sudipto Mukherjee, a leading robotist from IIT Kanpur, give us a brief reaction to the presentation of Professor Vijay Kumar and the discussion, and share with us his thoughts on the implication of today's discussion on Indian education and Indian technological innovation. Let me please begin by requesting Shri Rahul Gandhi to come up and kindly share his thoughts with us.
Can I do without this, or do I need this?
Anything.
I'd like to welcome Mr. Vijay Kumar and all our friends here. I've been pestering Mohan that we need to sort of look at the technological side as well. And I'm very happy, Mohan, that we finally got an eminent Indian to come and talk to us about that. I'd like to give you 2 minutes of my perspective. This morning, I had a meeting with some Arab ambassadors, 12-15 Arab ambassadors. And I woke up, 12-15 Arab ambassadors came to me this morning and they said, what's going on in India? I asked them what's going on in the Arab world. And they turned around and said, what's going on in India? I said, no, I want to know about the Arab Spring. They said, no, we don't want to tell you about the Arab Spring, we want to hear about what's going on in India. There were many people there from the new sort of regime, and there were some people there in the old regime. And I told them, look, what is happening in India was triggered off about 100 years ago by Mahatma Gandhi. He came here and he gave us political expression. And whatever we've done since then,
has happened as a result of that fact. He built up a structure that allowed us to express ourselves politically. I said there are three basic forces that are driving the change in India. I said essentially what is happening, and Mr. Vijay Kumar will understand this much better than me, what used to be hundreds of thousands of little networks living in villages are now converging and becoming one network called India. And that network is connecting to the rest of the world as well. What are the forces that are driving this change? In my mind, there are three forces: democracy, migration, and technology. And I'm happy to have Nandan here who's sort of working on the migration piece. What has happened is hundreds of thousands of little networks in villages are now exploding and breaking open. Information that used to be locked up inside the villages is now coming out. And what you're seeing in India, what people call this entrepreneurship, what people call this progress, is basically the formation of this network and the cracking of those silos into one big network. I don't want to keep you for too long because there's someone much more interesting than me, but I want to give you one last story. Some years back, I was in Italy and I had gone to visit the Fiat technology labs. And in the labs, there were a bunch of students there who were working on automobile design. I started talking to them. And I said, listen, what keeps you awake at night? You know, what worries you? You're going to be going into this new environment, into the job environment. What is keeping you awake? And in a second, one of them said, you know what's keeping me awake? It's those Indians and Chinese people. They're keeping me awake. And I asked them why. What is it? Why are they keeping you awake? And he says, well, because those Indians and those Chinese, they'll work all day. You know, I'll work 8 hours and I want to go home. But those guys, we have some of them here from China and some of them from India, they just work 24 hours a day. I said, I understand that they work 24 hours a day, but what is it? Why is it that they worry you? What is it about them that actually worries you? And what has happened? Why is it that these Indians suddenly and these Chinese suddenly are at your gates and they're disturbing your peace? And I asked a couple of them, didn't really get a good answer. And then one fellow in the corner, he turned around and he said, I know exactly what's happened. And I asked him, what is it? And he said, you see, Mahatma Gandhi and Chairman Mao unleashed the Indian farmer. They opened up the Indian farmer and they released the Indian farmer from his land. And he is now transformed and is standing at our gate. Mao did it very differently. Gandhi did it very differently. Mao and China paid a human cost. We didn't. I believe we did a more effective job. Of course, we have our issues. But essentially what I'd like to, who I'd like to introduce here is one of those people that Mahatma Gandhi unleashed, Mr. Vijay Kumar. Do I go there? I come down.
Thank you, Mr. Gandhi, for your remarks. We'll now have the main talk of the evening to be delivered by Professor Vijay Kumar, UPS Foundation Professor, School of Engineering and Applied Science, University of Pennsylvania. May I now invite Professor Kumar to kindly come up and deliver his talk. We are also happy to inform you that this event is being webcast live. Thank you.
Thank you. I want to thank Mr. Gandhi and Dr. Gopal for inviting me. This is really a pleasure to have this opportunity to share with you some of the work that my students and I have been doing at the University of Pennsylvania.
Light off.
In the next 45 minutes or so, I want to tell you about aerial robot swarms. But before I get into today's discussion, I thought I would start with a really short history of robotics. I recently turned 50, which means I have the license to tell you about history. And I also have the license to show you some black and white pictures. If you look in this picture, the gentleman on the right is George Devol. In 1954, he was awarded a patent for the first programmable automation device, which eventually became the Unimate robot, which you see on the top left. And the gentleman to the left is Joe Engelberger, who, along with George DeVol, started the first automation company called Unimation. And the first industrial robot was installed in 1961 by General Motors for handling die-cast from the assembly line and transporting this die-cast near auto bodies and then welded to auto bodies. So this was 50 years ago. In the last 50 years ago, industrial robots have matured. The first 20 years saw them mature and find applications in factories. And this technology finally found its way into medical robots. The Da Vinci surgical robot is largely based on this technology. The next 20 years saw the advent of mobile ground robots. So instead of industrial applications where the application had to be brought to the robot, for the first time now robots could go to the application. And this 20 years or so saw the advent of self-driven cars. I'm from the University of Pennsylvania, so I'm obliged to show you a car developed at Penn called Little Ben. Penn was founded by Benjamin Franklin, so everything at the university is named after Ben. And this is one of our smaller cars, so it's called Little Ben. Of course, the car that really epitomizes self-driving cars are the Google cars, which looks very similar to the car that you see here. So I'd like to think that the next decade is really about aerial robots, where now robots are able to go to applications not just in 2 dimensions, but in the 3rd dimension as well. And there are 3 drivers for this work. First, of course, is the enormous increase in unmanned aerial vehicles. So if you look at this chart, you'll see that there's a 100-fold increase in aerial vehicles every decade. And so now it's a $20 billion industry. Approximately $10 billion really comes from the military, mostly for surveillance and force protection applications. And a lot of this started in the US after 9/11. But there's a lot of civilian and commercial interest. Transportation, environmental monitoring, farming applications. In fact, recently in the US, the Congress mandated the FAA to have UAVs share the national airspace along with commercial planes. The biggest impetus for this actually comes from the civilian do-it-yourself community. If you go to this website, DIYdrones.com, you will see thousands, if not millions of users that are now developing little components of UAV technology that are being open sourced and essentially lowering the barrier to entry to this field. And again, a lot of this has been popularized by the availability of really small, low power, inexpensive sensors, high-end processors, GPS, and again, the availability of all of this technology for people who want to develop UAVs. The second driver for this work comes from the fact that these UAVs are getting smaller. So in this picture, you see on the right side the big monolithic aircrafts used by for military applications. But on the left side, you see UAVs that we're developing. So these are handheld UAVs ranging from about 1 meter in diameter all the way down to 20 centimeters or so, weighing about 2 kilos on the high end, all the way down to 75 grams at the lower end. The third driver of this work really comes from the fact, and Mr. Gandhi talked about this, there's not only networks of people, but networks of robots. And what I mean by that is really applications with large numbers of network computers, network sensors, network processors, and machines. And you can see it in automatic platooning by Volvo. They're developing commercial fleets that are unmanned. Certainly in military applications, mining applications, manufacturing applications. My favorite, though, is this example from Kiva Systems. And let me play you this video where you're going to see hundreds of robots in a warehouse. And some of you may know that Amazon recently bought out Kiva Systems. So these robots are able to autonomously navigate, coordinate actions to avoid collisions. When a human operator, you see that the person on the top, on the left side of the screen, you saw that a minute ago. When that person asks for an order to be filled in this warehouse, she does not know which robot is going to respond, what pod has her order, how that robot is going to go to the pod, pick it up, and then bring it to her. All she knows is that she commands the swarm of robots with a fairly high-level request, and that request is always met in a timely fashion. What we're interested in, though, is developing networks of aerial robots, and more precisely quadrotors. So these are robots with 4 rotors, and therefore they're called quadrotors. And one of the reasons for pursuing these designs is because smaller truly is better. So if you look at the characteristic length, R, of this robot, you'll find that because the mass and the inertia of the robot scale as the cube and the 5th power respectively of this length, you'll find that the effective ability of this robot goes as 1 over R, which means the smaller you make it, the faster these robots can accelerate. And more importantly, the smaller you make it, the angular acceleration, the rate at which the robot rotates, differentiated once, goes as 1 over R squared. So that means these robots can be really agile, and you'll see this in the short video, where we have a smallest robot, a 21 centimeter, 75 gram robot, which consumes 15 watts of power, performing flips. So these flips are performed in less than half a second, and the robot accelerates from 0 to 2,000 degrees per second during these flips. And there's an onboard processor that computes precise commands to the 4 motors 600 times a second to make this possible. A slightly larger robot, and again, my former students have established a company called KML Robotics, and this is a slightly higher end version of the same platform. Again, 4 rotors. The big difference here is there's a GPS on top and a ARM Cortex-A8 processor that does some of the high-level computation. And on the bottom right, you can see the surveillance video, which is actually being used for inspection in an industrial setting. So this robot uses sensors on board, accelerometers, magnetometers, gyros, to sense its orientation, to sense its translation, and compute commands to these motors to determine how to direct the robot to get more information. So what I'd like to do today in the next 30 minutes or so is tell you a little bit about the challenges we face in developing it. I'm going to start by telling you about how we control it and essentially a quick introduction to the physics of these devices. A big problem we face is in getting these robots to determine where they are in the physical environment. This is the problem that we call localization. Third, as you scale things down, one of the big things you have to circumvent are the constraints that are imposed by reduction in weight and then the resulting power. So smaller is not always better, and so that's introduces some constraints, and I'll tell you how we deal with these constraints. And then I want to tell you how we're approaching this problem of deploying large numbers of robots and applications for these robots. So let me first start by telling you about control. So very briefly, as I said before, a quadrotor has 4 rotors, and you'll see that opposite pairs of rotors rotate in opposite directions. So 1 and 3 rotate in one direction, and 2 and 4 rotate in one direction. If all these rotors rotate at the same speed, the robot hovers. If you want it to rotate, all you have to do is take one rotor, spin it faster, generating more lift on the left and less lift on the right, causing the robot to turn. And you want to turn it the other way, you do the reverse. You rotate the rotor on the right side with a higher speed and the left side with the lower speed, and you get the robot to pitch the other way. So this very simple physics is used by the robot to stabilize itself. So 600 times a second, it's sensing its orientation and then determining how to stabilize itself to a horizontal position when the robot is thrown into the air. So this basic capability is very important, and it has to be very robust in order for the robot to perform robustly. Translations, on the other hand, are a little more complicated. So if I want the robot to go from one position to another position in the horizontal plane to the right, what the robot first has to do is to pitch forward, rotate, accelerate in the forward direction, and then it has to pitch back to decelerate, and then flip back to level to a horizontal position. So these computations have to be performed on board really quickly, very precisely, in order for this to happen in a reliable fashion. So one of the challenges that we take for granted with wheeled cars, for example, is non-trivial here, which is how do you get from point A to point B? And part of the reason for this complexity is if you want to really write down all the equations that describe this robot, and don't worry, I'm not going to do that, these equations have to be described in a 12-dimensional space consisting of all positions, all orientations, and all velocities. So rather than do that, it turns out that there's an elegant transformation that you can do. You take this complicated 12-dimensional curved space and you flatten it out, reduce the dimension down to a 4-dimensional space in which you can actually transform the points A and B and find smooth trajectories that go around obstacles in the physical world. In particular, the trajectories we're looking at are called these minimum snap trajectories. The reason we minimize a quantity called snap, which, by the way, is a higher order derivative of position, is because we want the motion to be as smooth as possible and respect the dynamics of the aircraft. So once you find it in this lower dimensional space, which is fairly computationally tractable in real time, you transform it back into the complicated space and allow the robot to execute these motions. So even though I'm a mechanical engineer, a lot of what I do and what my students do is develop software. And there are 3 levels of software that are required for these robots to operate. As I said before, the most critical thing is this inner loop where you essentially try to control the attitude or the orientation. You have to sense the rotation using onboard sensors, calculate commands to the 4 motors, and then the propellers to regulate the orientation. The next loop that you have to worry about, and by the way, all of this is performed on board. The next loop you have to worry about is a position control loop, which again determines what rotation needs to be commanded in order to get to a desired position. And once more, you have to measure the position and compare it to the position you want to go to in order to execute this loop. So one challenge is, how do you get the robot to measure positions? One way of doing it is by using cameras. And in our lab, we have a system of motion capture cameras. So you see the infrared cameras on the top and the robot in this infrared capture room. It's receiving position updates 100 times a second in this position control loop. And then the outer loop is a trajectory control loop using the dynamics that I just described. And that is done on an off-board laptop, similar to the one that I'm using, which computes trajectories 20 times a second. And so you will see now a few videos that illustrate how the robot works. So this is my former student, Daniel Mellinger, who's throwing this robot into the air. Let me turn up the volume to give you a sense of sound. So regardless of how he throws it, this is the inner loop that's regulating the position. And the word basin of attraction is a technical term that basically tells you how robust the system is. So if you want it to stabilize from a larger error, from more wild throws, the larger that basin of attraction needs to be. And the key idea is if you shrink the size of the aircraft, you make it more and more maneuverable, and you make it more and more robust. So next I want to show you what these minimum snap trajectories look like. So you'll see the robot going from point A, going to point B, and then going to point C and stopping there. And here you will see the results of the computation of this 12-dimensional space, then warp to the 4-dimensional space and going back again as the robot executes this minimum snap trajectory. Again, this is completely autonomous. There's no handcrafting involved. In fact, it is very, very hard to fly this robot with a joystick. In fact, in our lab, we don't have joysticks. They're practically useless. The same thing you can do with these in the presence of obstacles, and you'll see this robot now going through these hoops that were placed in the environment. The robot knows where the hoops are, and so it can plan these minimum snap trajectory through the hoops. It doesn't matter if the hoops are actually moving. It can find the hoop and then execute a trajectory through the hoop. And again, these computations are done on the laptop between 20 to 40 times a second, and then by the cameras 100 times a second, and then on board 600 to 1,000 times a second. Another thing the robot can also do is take segments of trajectories that it's learned and then stitch them together. So here you have an example of a robot that's trying to go through a window that is barely wider than the height of the robot. The only way it can do it is by taking its attitude and flipping it by 90 degrees to go through this window. So much like a diver can jump off a diving board and gain energy and then twist her body into a somersault, this robot does effectively that. It first gathers momentum, as you'll see, and then flip its body around to go through this window. And it actually takes these trajectories that it has learned and then stitches them together. So again, you gather momentum, you change orientation, and then you recover back to a hover position. So in all videos, you saw the robot performing in a very, very carefully controlled laboratory environment with motion capture cameras on top. When we go into the outside world, we don't have motion capture systems. If I wanted to deploy the robot here, I wouldn't have these cameras. And the only thing that stops us from deploying the robots here is this problem of localization. I don't know where I physically am in this physical world. So our first attempt to solve this problem without onboard cameras came in this form, where we took one of our quadrotors, we put two key sensors on board. So one is a laser scanner that sends out laser beams through a 270-degree arc and gets reflections back so you know where different points are in the environment in the plane of this laser scan. The other piece of hardware, which you can now buy with an Xbox, is a Kinect platform. This is a color depth camera which gives you a cloud of points between 3 meters away and 5 meters away. So all of a sudden now the robot has 3D vision on it, on board, and it can actually start sensing the environment. And we can take the same software architecture that we had before with the 3 nested loops and do all the computations with onboard sensors. How does this localization work? Well, let me show you how we estimate the position and orientation with a little cartoon. So imagine you have a robot in the 3-dimensional environment, and imagine there are 3 pillars in the environment, but it knows nothing about the pillars. It doesn't know where it is, and it doesn't know where the pillars are. But it does have this laser scanner. So the first time you make measurements, it identifies where these pillars are and how far they are, D1, D2, and D3. When it moves to a new location, through a small displacement delta x, it's now at a new position, and now the laser scanner gives it 3 new pieces of information. Once you have all of this, the rest of it is really high school trigonometry. You have multiple variables that are related through geometry, and all you have to do is solve for all the unknowns. And what are the unknowns? There are 8 unknowns, the 3 pillar locations and the 2 variables that tell you how far the robot has moved. So not only have you figured out how far the robot has moved and localized the robot, but you've also mapped the 3 pillars. So you have simultaneously localized and mapped. And this begs the snappy acronym SLAM, right? So if you solve the SLAM problem, essentially what you have done is figured out what the room looks like, and you also figured out where you are in this room. And the robot has to do this 100 times a second because there are no motion capture cameras in this world. And here's how that looks. So here's the robot taking off and going into a building it's never seen before. And on the left side, you will see what the operator sees sitting outside the building. And the operator is essentially commanding this robot to enter the room. And you can see the map that's being generated on the left side as the robot navigates a fairly constrained environment in the interior of this building. On the top right, you see what the cameras actually see. But the key thing, again, are these laser scanners that essentially allow it to construct this 3-dimensional map that you see in the bottom left. Next, I want to tell you a little bit about the weight and power constraints. I started off by saying, well, we want to make smaller robots because that makes them more agile, more maneuverable. So if you look at this, the number one problem we ran into is to replace the motion cameras with onboard sensors, we had to put a laser scanner and then this Microsoft Kinect sensor and this is additional payload. And that made us use bigger motors, which in turn made us use bigger batteries. And of course, bigger batteries are heavier, so you need even bigger motors, and then even bigger batteries. So you run into the scaling problem, and then you end up with this fairly large robot which consumes almost half a kilowatt of power. Right? So that's unconscionable. But I'd like to tell you why. So here's the power story, and this is the most depressing part of anybody who does anything with mobile anything, right? You know, when you have phones, laptops, power is always a problem. With the best technology we have, lithium polymer batteries, if you look at the specific power, which is the power per unit weight, and specific energy, the amount of energy density in a battery, and here I have data points of batteries that we explored just for the use of building these quadrotors, and we assumed we didn't have to fly for more than 10 to 20 minutes. And the 3 robots whose videos I've just shown you are here, and you will see uniformly they consume a lot of power. In fact, if you look at the y-axis, you'll see they consume at least 400 watts of power per kilo. So that's a large amount of power. The other thing you'll see is that the batteries fall in this very, very narrow band. There's virtually nothing to the right side. It's instructive to compare this chart with what biology has to offer. So here's a picture of adipose tissue, fat. All of us have some of it, some more than others. And you'll see that this piece of adipose tissue is off scale. You look at the energy density, it's 10,000 watt-hours per kilo. If you look at the specific power, and here you can take your favorite athlete and ask, how much power does your favorite athlete produce? So for example, if you look at Usain Bolt, he produces maybe 2,000 watts of power and he weighs a little less than 100 kilos. But he only does it at 10 seconds at a time. And we're talking about 10 minutes or 20 minutes. If you look at Lance Armstrong, maybe he's not a good person to talk about today, but he consumes perhaps 6 to 7 watts per kilo on a sustained basis, 20 to 30 minutes. So the solutions that nature has to offer are just completely off scale, and we're nowhere close to that. In fact, the only example I can offer from nature that remotely comes close to the machines we use is the hummingbird. So the hummingbird is the only bird that actually flies like an insect. It flaps its wings to hover. Like our quadrotors hover, and in fact any kind of hovering device has the same kind of energy limitations and power limitations. So the hummingbird consumes about 200 watts per kilo, and all of a sudden our quadrotors that consume 400 to 600 watts per kilo don't start looking much better. But this is a problem. Anytime you build a hovering device, you run into the scaling problem. So what's the solution? Well, the solution is you make your robots lighter. And so we have to put our robots on a diet. So what's the best way to put our robots on a diet? Well, you take off the heavy sensors like the laser scanner. So here I show you a picture with 2 cameras. This is the simplest form of sensor that you can use to triangulate features in the environment the way the laser scanner does. And actually, if you look at any smartphone, in particular the iPhone, it has 2 cameras. It has a GPS on board. It has gyros. It has an IMU. It has pretty much everything that you need to fly except the propellers. So this solution is starting to approach something that we always wanted to do, which is to put wings on our iPhones. So this robot is able now to fly autonomously. It's not quite as lightweight as the iPhone, but you can see this robot without any special markers flying. This is inside our lab. This is outdoors. In fact, in this video, you'll see the downwash from the propellers on the bushes. And on the bottom right, you'll see features similar to those pillars that I showed you in the schematic that are identified by this robot 25 times a second, and it's triangulating off these features, figuring out where it is with respect to the features that it sees. And this video shows, on the bottom right, you will see the video from the robot's viewpoint. So again, you see the features. Again, there are 2 cameras. The green features are seen by 1 camera. The blue features are reinforced by the second camera. But you can see this robot now pitching and rolling to about 40 degrees, traveling at 3 to 4 meters per second in our lab. So this is not quite as small as where we'd like it to be, but this is critical in order to make lightweight, swarm-like robots. So I want to move on and talk a little bit about our approach to building swarms. But before I do that, I want to motivate the fundamental problem in replicating these and coordinating many, many of these. So here's a toy example. So suppose I told you that we want to guide 3 robots to their goals. In fact, I'm not going to tell you which robot needs to go to which goal, but I'm going to tell you there are lots of obstacles, and robot 1, 2, and 3 need to go to one of the 3 goals, each one. And so there's the first question is, where is the goal for robot 1, for robot 2, for robot 3? And there are many permutations. In fact, the number of permutations that you get grow as a factorial of the number of robots. But once you decide which permutation, you want to plan these trajectories. So what's the complexity of this task? So let's assume there are n robots, where n is a very large number, and m obstacles, where m is again a very large number, very complicated environment. So the first thing, which should be pretty obvious, is that space I told you about, it grows linearly with n, right? And so in terms of numerics, in terms of computation, the growth is order n. The more robots you have, the more computations you have to do by a factor of n. Worse, the number of neighbors that you have goes n squared. You know from social networks, the larger the network you belong to, the more complex that network is. The more complex it is for you to manage your interactions. That goes as n squared, the number of edges in your network. The number of potential interactions with obstacles goes as n times m. So you look at the complexity of this, and it's m times n plus n squared. And remember, m and n are very large numbers. So this goes quadratically with the number of robots you're trying to build. And then finally, the worst thing is the number of assignments. So remember, I have to decide which robot needs to go where, and that goes as n factorial. So if I put these 3 things together, n cannot be a very large number. In fact, n cannot be more than 2 or 3 if I just combine all of these things, no matter what processor you bring to the table. Well, nature solves it completely differently. So here's a picture of Phenogaster coccarelli ants in the desert in Arizona carrying a piece of fig. These ants are good at cooperative prey retrieval. So if they find prey, they bring it back to the nest for the young to feed. And so you'll see in these ants, there is no evidence of any kind of planning, no 12-dimensional space that these ants are thinking about. In fact, these ants don't even have a leader. Each ant is making its own decision in a completely decentralized way. It's based only on local information. And finally, there's this paradigm of complete anonymity. They're agnostic to who their neighbors are, right? The complete opposite of the social networks that you and I live in. And in fact, we've spent quite a bit of time studying these ants, and I want to show you a funny video. You can actually coax these ants to carry anything, provided you coat that with fig juice. And so here these ants are carrying an elastic object. And in this picture, you can see the elastic object deforming, and that tells you which ant is pushing and which ant is pulling and which ant is just goofing off and doing nothing. And there are many that are doing nothing. So we use this to study the roles of individual ants and how they signal each other. And we are using that to build better algorithms for swarming robots. But enough about ants. Let me show you a video of a team of 20 robots negotiating complicated environments and solving some of the problems that I told you about in terms of scaling up computations. So here's our 20 robot swarm. This is in an indoor environment, and they're essentially maintaining precise positions, relative positions with respect to their neighbors. They're tracing 2-dimensional, 3-dimensional formations, changing formations on the fly, and when they're confronted with an obstacle, they reconfigure their formation to fly through the obstacle back to the original formation. Again, all this is happening with a combination of onboard computing and off-board computing and coordination between these robots. And here you'll see this figure 8, where these robots fly really close to each other, coming propeller tip to propeller tip, precisely controlling their interactions. So I want to conclude by talking a little bit about applications. what might we do with such swarms? Well, one of the biggest missions we'd like to conduct is what we call an exploration mission. So here's one of our bigger robots entering a building, and this time there's no human operator. We release it inside, and it's a three-dimensional building. We tell it to go in and tell us what the interior looks like. There's no involvement, again, with any human operator. And you can see that the robot is actually figuring out where to go in order to get new information. So it looks at this map of information and determines what would be the next most fruitful step. And it's doing that in addition to doing the mapping that I showed you earlier. So why might you want something like this? Well, you can imagine that there are many kinds of disaster response missions, search and rescue missions, or terrorist operations where you might want to just enter a building to see, who's where the victims are, where the bad guys are. So this is sort of a very fundamental enabling tool, which we can now do with one robot, but we really want to do 10 times as quickly with 10 robots, or 100 times as quickly with 100 robots. One of the things we've really tried to do in a realistic setting shortly after the earthquake in Japan, so this video was shot in Sendai in July 2011 in a collapsed building, and you can see this robot riding on another robot made by our Japanese collaborators in Tohoku University. And one of the reasons we like this collaboration between an aerial robot and a ground robot is because, as I told you, the aerial robots are power hungry. So whenever possible, they try to hitch a ride on the ground robot. But of course, when the ground robot gets stuck, it releases the aerial robot. That goes in and does the mapping inside. And here's a bookcase that was impossible to cross, and the robot just flies over that bookcase to see what's on the other side and comes back, all the while creating a map which is then displayed to the operator on the bottom right. So using this technology, we were able to go into this building which had 3 collapsed floors, the 7th, 8th, and 9th floor, and navigate environments like you see here. And here's the kind of map that you can build. So you can see the 7th floor in green, and then the 8th floor in orange, and then the 9th floor in red. And some of these maps now can be created autonomously. Again, this experiment took us 1.5 hours to complete. We'd love to be able to complete it in 5 minutes. Another application we're looking at is construction. So here you see these robots grabbing Lego-like modules with magnetic fasteners. So these are truss-like elements. The robots are presented a blueprint of the structure they need to build. And here you'll see 3 different sped-up videos of robots building different structures. And again, in this, the key thing is that the robots are figuring out who needs to go pick up what part and assemble it to what piece, while negotiating a common airspace, avoiding collisions, and doing it optimally. Another example of a cooperative task you might imagine is just picking up things and moving it. As we build smaller and smaller robots, the payload carrying capacity of these robots decreases. And obviously what we'd like to do is to be able to carry big pieces, but by collaboration. So here you'll see robots coming in, coordinating to pick up an object, and they have grippers with nails at the end, so they can actually dig in and pick up things. And this is actually a wooden plank that's able to pick up, that the team is able to pick up and move. One other application that I think has interesting relevance to our society is just entertainment. Here you see 16 robots carrying mirrors, coordinating with 16 laser lights driven by independent actuators, all choreographed to music. This was at a very large marketing event organized by Saatchi & Saatchi in Cannes in France. And again, the key challenge here is to take the swarm of robots and have it interact with music created by humans, with a light show created by humans. And everything is, again, explicitly coordinated. So while we're in the subject of entertainment, let me share with you a clip from a a late-night comedy show shot in the U.S. In January 2011, and the comedian here is Stephen Colbert, talking about our robots.
For years, I have been warning about the threats of robots rising up against their human masters. Well, now scientists have reached a new milestone in our enslavement. Flying robots that can autonomously assemble magnetic rods into simple cube-like towers. There's no remote control here, folks. These buzzbots have a hive mind of their own, and apparently the first step to enslaving us is building dorm room shelves. Which brings me to threat number 2, flying robot drones. Folks, today they're constructing a 3-foot tower. Tomorrow it's a sprawling prison for 3-foot prisoners. Provided they can build it before their batteries run out. And it can't be too windy. And even if they don't enslave us, they will crush us at Jenga. Vigilance!
So I thought it was instructive that a comedian was able to pick up on the 2 key limitations of this technology, power and wind. And we get a lot of emails criticizing us for building what people think of as military machines. This is far from being a military machine, and I'm glad somebody saw the humor in all of this. The other thing I want to point out before I close is that the technology is something which is still at a very nascent stage. We're constantly experimenting, and there are a lot of failures, and I want to show you some failures. And it's important that we talk about failures because we learn from all of these failures. So here's a montage of quadrotor failures, and our policy is we film everything because sometimes it just works. So here are these failures. So the robot trying to land, and it doesn't see the perch properly, and it falls down. Picking up things is really complicated. If the robot doesn't know the physics, it breaks. Bad localization. It's trying to perch, didn't know exactly where the perch was, and it failed. This is just bad planning. So we rely heavily on communication. Communication's flawed, the whole swarm collapses. It's too complicated. Never do that again. This is what we call extreme robotics. The quadrotors are amazingly robust. One of the things I didn't emphasize is it's all built from COTS technology and integrated to keep things really, really simple. The only things that can get harmed are human fingers, and that's why we do these things in a net. So let me just conclude by making several overarching points. I hope you'll agree that by building really small and agile robots, it leads to exciting opportunities and interesting applications. And one major thing that we have to struggle with are these size, weight, and power constraints, and that may determine the kinds of missions that we're able to execute. By having these robots cooperate and to form networks, they enable novel functionality, in fact, functionality that we may not even have thought of. And then finally, and this is not always obvious, but although we make physical things, you cannot underestimate the role that software plays. And this is important, particularly in a country like India, where in fact software is one of the things that does rule. So we estimate that 80% of the value we add is really in the software and the smarts. So I'd like to conclude with a picture from a 1978 horror movie adapted from a novel by Arthur Herzog. Some of you may be too old to remember this, but everything about this poster is true. It's about the killer bees attacking humans. And if you look at the caption, this is a Warner Brothers movie, its size is immeasurable, its power is limitless, its enemy is man. The only thing I would disagree is the politically incorrect statement, its enemy is human, right? And the reason it is the humans are enemies is the swarm is coming, this technology is here, we're going to build it. What we don't know is how we're going to use it. So in some sense, its enemy is humans because we don't have the imagination yet to figure out what we're going to do with this technology. So with that, I'll stop, and thank you very much for listening.
We have about 45 minutes. Please, the audience may ask any questions.
Check. Hold on.
Here I'm with a team. It is from Delhi Technological University, which was formerly Professor Vijay, working in mechanical engineering with young team members. Very good. Yes. So, we were working on unmanned aerial vehicle and unmanned aircraft system for about 4 or 5 years, and we have shown our presence at various international competition level for innovative new instruments contribution. And very recently we are going through your paper on towards a swarm of agile micro quadrotors, which has created interest in people to put our hands into swarm robotics. So in this context, some of my UG students were along with me. So we started working on this particular project on swarm robotics, particularly with an intention of taking a problem related to mining accidents. This is our general target at this point of time. We have started that 2-3 months back. We are going through the literature review at this point of time. So my tech friends have got some doubts to get clarified. At the same time, from my side, I would like to know how well we can use the artificial neural network, genetic algorithm, and following optimization technique, all these things to bring in intelligence into these swarm robots. Thank you.
Thanks for the question, and it sounds like you're doing really interesting work. There are different methodologies for embedding intelligence, and the 3 methods that you mentioned are examples of methods that could be used. The one thing you really have to think about if you have robots flying in the air is to use methods that lend themselves to verified performance and robustness. You don't want things flying out of the sky, falling down on you, and it is unclear whether some of these techniques actually do work. So the ones that we use are slightly different, and they're ones that are accompanied by proofs of stability and robustness, and this is something that we emphasize in our work.
Second, you've got this imperative for miniaturization, making it lighter because of the power consumption factor. But surely the lighter and smaller they are, the less they can actually lift or build. Sensor technology, if so, have they been fixed? Because they all seem to be doing the opposite of what you showed us earlier they were capable of doing. Second, you've got this imperative for miniaturization, making it lighter because of the power consumption factor. But surely the lighter and smaller they are, the less they can actually lift or build in the construction and transportation applications. Isn't that going to be a shortcoming in terms of their utility? And third, when it comes to possible applications in a hostile environment, military, anti-terrorist, whatever, wouldn't you have a position in which, okay, let me put the other way around, how easily interceptable are they? They do make a noise, so they can be detected. Can you reduce noise? I'm not sure that's possible beyond the point. And how sophisticated is their ability to avoid anything from a human hand trying to swat them down to somebody trying to bring them down with a weapon?
All great questions. Let me go in reverse order. Remember the last one. So clearly, they're not designed for clandestine. You have to make them smaller. And the way to work around the issue of robots not having enough sensors is you have lots of them. So when you have lots of them, each one senses one little piece of information, And again, we have the technology to put things together. And that's where the value added comes in terms of software. So if the robots can communicate with each other and then they can actually do the computations, they can fuse together a cohesive picture of what the environment looks like. The first question you asked me is about robustness. So I showed those videos. Those were shot early on in our experiments to show you that we make mistakes. So oftentimes these videos are released in YouTube and everybody looks at this and say, wow, this technology is going to change the way. It's absolutely true. It is going to change the way. But I just want to point out that some of these experiments, some of these methodologies are hard to develop. And I just wanted to give you a flavor of that. But each one of them, we know exactly why it failed, and we learned from that. And if you were to come to our lab today, we could do the same things, and you won't see those crashes.
Professor, I am from Philosophy of Physics from St. Stephen's College. Hi, here. Bhupender Maite. The 2D space into X, Y, Z, and psi. I don't know whether what the psi was, whether it was T or not. My simple query is this. You are trying to show the 12-dimensional space over there. So how can we ever view it? And I would like to know that how have you done the calculations? Because even in string we use the light cone physics coordinates, because the mere coordinates of space and time we don't use it. So what sort of coordinates that you are using there, and how come you have calculated in the form of 2D? And if it is 2D, normally we have the compactification like Chalabi-Yau manifold compactification. So how can we ever see with our so-called human eyes, which works in 4D, that the video that you have just shown there? So I just want to get this clarification that what's all about. How have you done the calculation that is of 12D space?
So this is complicated to explain in a informal Q&A session like this. But I mean, at a high level, we use roughly the same tools that string theorists use. These are the tools of Riemannian geometry, coordinate-free representations, and you can never try. It's hard to visualize them. But what you know is that these constructions are correct, provably correct just by construction, and this mathematical equivalence that allows us to establish that if we do things in this lower dimensional space, it's going to carry faithfully over to this higher dimensional space. If you wish, I can talk to you afterwards and try to. I think this is going to require a piece of paper and pencil.
Professor, I'm not a science student here. I'm not a science student. Only one thing I want to ask: how many times an average thing to do a new thing, you fail? That is average for a new thing to do to achieve the success. How many times you fail?
This is hard to say, but what I want to emphasize is that over the years, these failures have allowed us to establish a methodology, a set of tools that make it possible for us to actually verify that everything works in a software environment. This is one of the key things in development. So you only want to do physical things once you're convinced it's going to work. And because of failures, these software environments get better and better over time. So the likelihood of failures actually keeps going down. So when we first started, that window experiment I showed you failed 3 times. But again, we were able to learn from each one of those experiments to refine it as we went forward. And in fact, there's this iterative learning algorithm that the robot uses to constantly improve its estimate of what it's doing and how to actually adapt to uncertainties.
As a student of social science from University of Delhi, and having heard the talk of world youth leader, I'm sure Sri Rahul Gandhi the other day during his election trips, he said that his guru is Gandhi, and we were so happy about this. When we are talking of Gandhi, we must not help but remember his name on this auspicious occasion. When we were interacting with Mahatma Gandhi right now, what would his reaction would have been under the circumstances when we are already being overawed by plenty of such technological advancements and equipments which have enslaved us to the level where we only require a leader like Rahul Gandhi to retrieve us from that particular situation. This is one. And second, as once again a student of international relations, I will say what happens when such a robotic exercise falls in the dirty hands of the terrorists, by the way. Thank you. I shall like Rahul Mr. Gandhi to make a statement on this.
I think it's for you.
It's for me.
Thank heavens it's for you.
Oh, well, I'll attempt that. I think technologies are what you make of them, how you use them. And I was discussing with Professor this afternoon, this technology can be used by, well, as in Professor's words, the good guys, and it can be used as the bad guys, used by the bad guys. But I think what's important is how you choose to use it. It's a dangerous technology. I mean, I was mentioning to Professor Vijay Kumar, if you look at what is going on in Iraq and Afghanistan, it is essentially a social network coming into contact with the mobile network that is allowing terrorists to attack, for example, the United States using IEDs. Right? The use of explosives in Iraq and Afghanistan has been transformed because it is being done on the back of a mobile network. So it's true that these technologies will be misused. Professor's answer to me was that it's better that we learn to use them up front and we try our best to understand how they can be misused rather than ignoring the fact that these technologies exist. That's the answer to your second question. The first question, I think, I don't think technologies enslave us. I think we enslave ourselves, you know. And I think Gandhiji's view was pretty simple. Try and ensure that whatever you're doing is benefiting the last person in the line. For me, the reason I called Professor and I got in touch with him was because many years ago, when we spoke about computers, when Sam Petroda and my father spoke about computers, everybody responded in a negative manner, saying that, look, what have computers got to do with our future? This is the computers of the 21st century. This is what computers were 30, 40 years ago. And the reason I invited Professor here was to tell us, how should we think about this? How should India, the largest democracy in the world, fast growing, fast moving, think about this technology? So I think it's a very powerful technology, but we need to understand it, and I'm happy that you're here to help us understand it.
I have an easier question, I think. Since Mr. Gandhi started with agriculture, and agriculture is so important to all of us here in India and in fact to the rest of the world, perhaps you'd be able to tell us something about the application of this specifically to agriculture, and that is specifically in India.
I do. So before I get into this specific technology, I do think that agriculture is one of the world's biggest problems. So the predictions are that by 2050 we'll need an entirely new country the size of Brazil, fully cultivated to feed all the mouths. And the only way to get around this problem is by increasing the productivity, the per square foot productivity of the land, and also in terms of water consumption, right? So I think robotics, by and large, has the potential of increasing productivity by a factor of 1,000 in this sense, by building vertical farms, for instance, and also reducing water consumption by a factor of 100. Specifically, what can aerial robots do? I think one obvious application is just monitoring of crops and spraying pesticides and so on. It's less clear that you can have aerial robots do something more in this particular space. But remember, when you have large farms, this is a lot of the problem. And I think there could be a big impact. And it's a relatively low-hanging fruit, no pun on that word, for this technology.
Can I just take a slightly different perspective on that? You see, it's not so important to figure out what the potential applications can be. I remember when I was in college, and one of my friends who I thought was nuts used to work on computers, and he was working on the sort of beginnings of the internet. I didn't understand it, I was skeptical of it. When a network builds up, whether it's the internet or it's a network of robots, it will have an impact on your world. You will not be able to predict what are the applications. I guarantee you there will be applications. When mobile phones first came out, nobody figured or nobody thought that, listen, these things will be able to predict our location and you'd be able to advertise using location. It wasn't, I used to work in that space in my consulting days. It was not on the radar. And suddenly the fact that you could locate a person changed everything. So what I'm pretty certain of, and I'm sure Professor will agree with, is that this is a network that is being built. Today it's robots, tomorrow it will be a swarm of robots. Essentially it's expanding a network. You have an internet, you move to the mobile phone, and now you're taking that network into space. It's going to have consequences. What the applications are, we probably, him better than me, I certainly can't predict. I think you'd find it difficult to predict. But what we both can guarantee you is that it will be phenomenal and it will have an impact.
Sir, good evening, sir. One application we can think of is like we can use it in earthquakes, where we can find the survivors and all. Then I would like to ask you a question. We can use it for landmines, since Princess Diana was working on it, we know that. And we find places like Vietnam and other places where a lot of landmines are still there, and Second World War landmines are still there. Can we use it to detect those mines in certain located areas where we can use it as an application?
Definitely. I think robots are being used today to look for landmines. And, a big problem, of course, is the sensors on these robots, because they're not very good at detecting landmines. But since these are landmines, it makes sense to use ground robots for the most part, or underwater robots if these mines are underwater. And one of the difficulties, you have to be flying really, really low if you need to detect that. It is possible, but it's unclear that at this point that represents the best bet.
Good evening, sir. Sir, my question is, you haven't discussed about the costing of such kind of quadrotors. Could you please discuss on that? How much this quadrotors cost, and how, economic they would be for a nation to adopt, or for the military services or such?
Well, the cost of any prototype is hard to predict. The cost of products, on the other hand, people claim that they can predict it, but actually it's determined by who wants it and how many of the products you make. But all I can say is that, again, I go back to my iPhone. My iPhone is much more complicated than that robot, and it sells for several $100s, right? So one should be able to make it at that price. But of course, there are a lot more iPhone users than Quadrotor users.
It's fascinating talk. Just an odd question. Your control systems seem to be not very hierarchical. That is, if you look at the videos of the 20 or so robots flying around in formation, one has the same position in a social network, if you will, as the other robots. And presumably they're all talking to a controller that controls all of them. I was wondering if you had come up similar to human management sciences, that perhaps humans cannot manage more than 6 people at one time, and that's why we get hierarchies. Whether the same kind of thinking perhaps applies in your space. I was wondering what your thoughts were.
That's a great question. One question is if we should actually be inspired by human-made networks as opposed to naturally occurring networks in nature. And in the latter, you have a lot more hierarchy to manage complexity. So we've looked at that, and although you didn't see it in the video, there was a little bit of hierarchy in the way those the 20 robot formation was controlled and the formation changed. The more interesting question, however, is if a completely flat society, a society devoid of any hierarchy, could function as efficiently as a society with hierarchy. And that's something we'd like to also explore. So the ant-like behaviors, if you will, are an example of that, where in fact you can show that a team will eventually reach consensus as they decide to do a task. And so there are these two parallel threads of research that we are pursuing. And again, I didn't have time to get into it, but you're absolutely right. This is a fascinating question and really worth more discussion.
Hello, I'm Biswal from Cluster Innovation Center, University of Delhi. I have a slight technical question. When you have swarm of robots, you have certain amount of computation on board, and you have certain amount of computation which is happening probably at a laptop or something, and there is a communication going on between the swarm of robots and the laptop. How much of the computation is happening on board, and how much is happening at the laptop, and how exactly the power is shared? And if one robot, for example, malfunctions, is that already also into the algorithm to take care of, and where is it actually distributed?
It's another good question. In a strange sort of way, it's related to the previous question about hierarchy. Again, there are these two paradigms. For 20 years or so of my life where I've done robotics research, I've always worked under, and my colleagues have too, worked under three key assumptions. One is that computing is finite, memory is finite, and data is finite, right? Today, all those three assumptions are flawed. If you look at much of the computing infrastructure, we always have access to more and more computation, right? Data storage is never a problem. So you always assume that there's a network and you can outsource whatever you cannot do on board to something else. So that's one paradigm of computation. So in that paradigm, I could shift almost everything to my laptop and only do the bare minimum on board. For example, the very, very high servo rate, 600 to 1,000 times a second servo rates, which have to be done in a time-critical fashion on board, and everything else could be off board. But at the other end of the spectrum, we still want to, for instance, when you enter a room with radiation and there are no communication links, everything has to be done on board. And so we're also exploring that end of things where every robot is completely autonomous and is completely self-sustained, like we are.
Good evening. So we admit that it's a great technology, and how about okay, the robots are in our control, up to that time it's good, but how about the thing that it's out of the control, and how can we control those robots?
I'm sorry, could you repeat that again?
Up to the sense the robots are in our control, it's good, sir, but what is the thing if
when it goes out of control?
If it goes out of the control,
we're all in serious trouble then.
like we are also robots made by Rahul ji.
Right.
Indian Youth Congress. But we are being controlled by Rahul ji, sir. Then just I wanted to know how about the robots made by you? Thank you.
Well, you don't know this, but actually he's a robot.
Exactly. Controlled by another robot.
Professor, it's a very interesting. I'm in the gallery.
Oh, thank you.
I think it's good that from gallery also the voice comes forward, I think. Professor, it's very interesting. Linked to the particular question that came up just now, maybe it's a bit of a philosophical question. What is going to be the impact in the long run? What is going to be the impact of this reliance on robotism on the human mind itself? Like, for example, now we have the robot that is, we give a script. And accordingly, I suppose the script, the robot functions. In a sort of a determinism is given to the robot. Now, in the long run, when the human mind in its creativity as well as in its production and also in its application also, what will be the impact of this sort of determinism on the human mind itself in our own relationships with regard to the use of our freedom? I suppose I'm making my point. So I just want to know, in the long run, what will be the ethical question that will be involved with regard to the freedom, the choices of the human person?
Wow, this is I don't know about the ethical questions. I mean, certainly there are a lot of ethical questions you can ask when you're trying to develop new technologies. Is it ethical or not? But I think you mean more as a user. And certainly when you're presented with a technology, how you use the technology changes you and also changes the technology, right, to some extent. So, I don't know, we've developed this amazing ability to be able to walk like this, right, which we didn't have. And I bet our peripheral vision out of the top of our eyes has improved enormously because of cell phones or smartphones. So that's just a simple behavioral adaptation to the technology. But anytime you deal with lots and lots of entities and coordinating lots and lots of entities, it really raises the question of what we mean by social networks, which right now consist of just people like us, but eventually could be people like us and machines. And so I think this is a great question, and I don't have an answer to it, but it certainly is going to happen, and we've got to be ready for it.
And what we can learn from nature regarding emergent phenomena and swarm intelligence. I'm also a bit curious to know if, for example, you've seen the implications of flocking, the other implications of flocking, not only collective behavior. For example, in birds, it's known that flocking helps prevent predators from easily catching the birds. So have you tried two different groups which are trying to compete, or one bad copter which is trying to catch the rest, and how robust is such a swarm to?
That's a great question. The one thing I do want to emphasize is that it's good to be inspired by nature, but it may not always be productive to mimic nature. So there are lots of things that nature does, and some of it may be relevant and some of it may not be. But in this particular case, the only thing that I can think of, and this is in connection with this question about defending against people who might use this technology in an adversarial sense. So the one thing we have talked about is how do you use a swarm to protect from one rogue aircraft. So it's actually very easy, using a combination of cell phone and UAV technology to have explosive on a robot that can be headed in your direction. And the one way to protect against that is by using lots and lots of robots. So this is sort of related to this, but again, the idea is that you want the swarm to be resilient with respect to individual predators, which would be that attack robot. And so that's one of the things that we've been thinking about quite a bit.
Good evening, sir. Actually, throughout the video, you have been using quadrotor systems, like quadrotor designs. Why not other designs like a helicopter or coaxial systems? Why not other? Why only quadrotors? That's my question.
That's another good question. I could take every design that you present and argue that this represents a better design in terms of use in indoor environments like this, in highly constrained environments, and in terms of high maneuverability. The other thing I like about this, again, being an engineer, you want to use things that are easy to put together. And so this represents our best bet today in terms of taking off-the-shelf components and reducing the intellectual effort to the integration of well-established components. Everything else, there are all kinds of other complexities in the components themselves. And this is one of the reasons we pursue this.
Good evening to Rahulji, Professor and all. Myself Arun Huda, President Delhi University. Sir, I am curious to know, are these capable of working in every environment, like in high altitude, or the environment is worse, like windy or etc.?
Probably not. I don't think it will work in space, for example.
Yeah.
High altitude, obviously, the air density will affect what you can do, but otherwise the technology should scale. I think one big problem is how do you function in environments with poor visibility? Yeah. Robots are particularly bad at that. If you use cameras All you need is clouds to obscure your visibility, and the robot will not function. If you use lasers, actually smoke is pretty bad in the infrared regime. In fact, glass windows are terrible, as they are for birds. They're bad for flying robots as well. So there are inherent environmental limitations when you develop these technologies.
So one application I've seen, these are building up structure and picking up the things. And can we imagine that soon the time will come, they will start picking up the things like guns and start firing as the humans?
So again, this goes. The head robot will make sure that never happens.
But that's a huge concern, actually.
Good evening, sir. This side. I'm Tarang Doshi. I represent the Young India Fellowship. So my question is, considering the disparity that India faces, how do you see the usability, affordability, and accessibility of such technology percolating downstream?
I'm sorry, the all-terrain.
How do you see it percolating down, this technology? The usability,
the accessibility, the usability, and the affordability of such a technology percolating downstream, like downwards.
Well, Rajiv ji talked about Rahul ji talked about the democratization of technology, and that's really what we're trying to get to. As I mentioned earlier, the components are all standardized, and the value added is in the software. So our whole goal is to take the barrier to entry and lower it to the point that everybody can start using it. So in everything that I described, you'll find all aspects of this documented and available so that others can replicate it. And I think this is one way of doing research. The more people start attacking these hard problems, so the sports metaphor is there's more shots on goal, the more you'll score, right? And so we need more smart people playing with these technologies to develop them further. And that's how I see this percolating down the stream.
Good evening, sir. So I'm a business economics student from Delhi University. So basically we are reducing the cost of the production and we are advancing in the technology. So the labor of the human labor is basically decreasing. So is it beneficial for the whole economy that we imply such an technology in our economy where we are developing country? Second question, sir, what are the basic demerits of this technology?
Sorry, basic what?
Basic demerits, shortcomings in this technology.
So I spoke about the limits, right? And so to me, it's I'm sorry?
Shortcomings, I think.
Shortcomings. So I spoke about the fundamental payload limits, the inability, actually Stephen Colbert talked about the inability to function in the wind, and then as you scale things down, the need to rely on communications. So those are some of the shortcomings. And associated with that, I should also point out the fourth one is the mission life. The smaller the batteries you carry, the less you can fly. So one of the challenges we have, and this relates to your first question, is what are the applications you can imagine that are consistent with these kinds of limitations, or can coexist with these limitations? So I mentioned a few applications where I think this technology is ready. In particular, I think exploration of hazardous environments after a disaster, I think that's something we can use today.
Sir, but that's the application. I'm talking about whether it's economical to use in a developing country right now.
So economical, I think, is a very complicated question. It really, again, has to do with the products that you're envisioning, the application you're envisioning, and the demand for that. And I think if you were to look at disaster response, there's no price that you can put on disaster response. Disasters will happen, and you have to be in a position to respond to them, whether it's economically viable or not.
Especially neurological.
So the question was, how can physically challenged people benefit? I'm not sure that they can benefit from aerial robots, but I do think robots have a big place to play in healthcare. I'm quite confident that by the time I turn 75, I'll have a robot in my house helping me. And I'm going to be programming the robot and having a lot of fun doing that. I don't know again about neurologically disadvantaged patients, but I can imagine simple tasks that robots can do today that can really help people in their homes. And the main barrier is not one of technological feasibility, it really is a question of economics. And so there'll come a point where I think this technology will be economically viable. And that's when we will see robots play a more prominent role in healthcare.
Sir, if you apply this technology, will it not affect the employment opportunities?
That's always the question that comes up when you talk about robotics, right? And I'm not going to deny the fact that there are jobs that robots will do that humans will not do. And usually the argument that people make is, well, those are the jobs that you don't want to do anyway. Those are the dull, dirty, dangerous jobs. But you cannot argue that with the human whose job has been replaced by the robot. So that argument doesn't go very far. So to some extent, this is going to happen, and I'm going to argue that it's inevitable. Because robots will be better at certain jobs than humans will be, and you will replace them. Right? So there's no point fighting it. The real question is, how can robots and humans coexist? And the right way to think about robots is robots helping humans perform jobs that they're good at performing. So I can think of great examples, for example, surgery, where humans are good at many, many tasks, but they're not good, for example, at doing high-precision operations after 3 cups of coffee. Right? But robots are very good at that. They're unaffected by how much coffee they drink. So that's an example where the complementary skills can play an important role without eliminating the human in the loop.
Professor, thank you so much for the wonderful lecture. Now, my question is, which ties into some of the questions that have been asked about the application. In absence of a well-defined roadmap or well-defined brief for where this technology is going to be applied, and clearly it's a groundbreaking technology, and one can imagine thousands of ways in which this could potentially transform the way we will live 50 years down the line, 100 years down the line. So in absence of, but still, it is still sketchy, the application part, and that was what was talked about by Rahulji also. So in absence of that, how do you prioritize your work in terms of where research and planning, in terms of, do you invest more in making the robots travel faster, being more precise, being more heavier, lighter? So which is the direction in which you will take the research? And second question is, who's at the moment, since commercially there's no application which seems capable enough of sustaining the research work, who's really funding the research in the Penn University? And would you advise that as a country, India should also perhaps take up this research?
I don't like these multi-part questions where each question is a good one, and then I have trouble following this up. But if you're in a university, your mandate is to do basic research, almost at the expense of applications. An even bigger mandate is to train people, and so education and training is really the top thing. So the questions we often ask when we're confronted with problems is, solving the problem, will that constitute a good thesis, a doctoral thesis, for instance? And that oftentimes is a litmus test in determining whether a project is worth pursuing or not. At the same time, if you want to raise funding, you cannot be blind to opportunities in the applications arena. But there, you have to be very careful, because if you pursue a product, companies are much better at doing that. They're better equipped at doing that. And so you really have to work with companies to do that. And this is something that universities worldwide are struggling with. There are no really effective technology transfer and collaboration mechanisms. Perhaps there are in India, but certainly in the area of robotics, I haven't seen any. And this is certainly a question to be thinking about. In terms of our funding, again, most of it comes from basic research. Basic research in the US is funded by 14 different federal funding agencies. The biggest one is the National Science Foundation. The Department of Defense has 4 different funding agencies. The one I like particularly is the one called DARPA, which is Defense Advanced Research Projects Agency. And one of the things they're able to do oftentimes is to pose research problems as challenges, as contests, allowing anybody and everybody to participate, and then rewarding people who actually successfully solve the problem. And if you go back and look 4 or 5 years ago, the self-driving car emerged from one of these contests. So from a government standpoint, it's a great way to sort of shape the debate. You throw out a challenge, that challenge suddenly has the national spotlight trained on it, and hopefully it's an important technology, something that people can relate to, and allows people from all over to compete and solve the problem.
Hello? Good evening, sir. The question that I would like to pose is that you said that most of the components in that nano were COTS, commercially off-the-shelf components, but on that small scale, on that 20 centimeter scale and 75 gram limit, is it really possible to get all those commercially off-the-shelf components for that thing? The second question which I would like to pose is that, for the SLAM algorithm, you use those big Aztec Pelican and Aztec Hummingbird quadrotors. Can't we use a quadrially developed component for quadrially developed helicopters like the one used by ETH Zurich, which also, I think, in terms of that particular size limit and that particular power consumption, isn't it more economical in terms of power and energy density to use that, use a quadrially powered systems rather than a quadrotor? And the third question that I would like to pose, which is probably the question for every budding engineer or every undergraduate student, is that if you need to get any more support
So to answer the first question, everything is based on commercially available components. And if you go to our website and look at the papers, it provides details. And if those details don't suffice, get in touch with me. I'd be happy to provide you the details. And as I told you before, I think the 4-rotor configuration, the quad-rotor configuration, is in fact, given the present state of the art, it is actually the best bet in terms of developing small, agile platforms, and better than the coaxial configuration that you refer to.
Good evening, sir. Good evening, sir. Good evening, sir. How much the maximum flight time during your research? And the second question is, can we operate your system on totally based on renewable energy?
The total flight time is between 10 to 20 minutes. The difficulty with this energy is that you really need not only energy, but also a very, very high power per unit kilo. And lithium polymer batteries work. It's very hard to imagine that high power, high power source comparable to that. The only thing I can think of are tiny rocket engines. That's another way of providing the power. But if I were to use solar power or something like that, I just would not get the required power. You get the energy, but not the power.
Thank you.
Now we'll take just 2 questions.
Yeah. Good evening, Rahulji. My question is, I'm sure this technology is good enough in helping to sort out problems which exist. But can this technology predict problems in the future? And if it can, how can it help solving it?
I'm sorry, you want technology that predicts problems?
Problems in the future.
Can this predict problems in the future?
This technology predicts future problems in future.
Like predicting future, like what? Like palm reading? No. I'm sorry, I'm missing this.
No, as in predicting probably earthquake. Probably cyclones.
Oh yes, yes.
Tsunami, something like that. You know,
Yeah.
something which is.
Can it be used for prediction?
Of course. So we've been approached by companies that are interested in geoprospecting. In doing earthquake testing is actually possible with aerial robots. But the other big one is actually environmental monitoring. If you have swarms of these flying, you can detect microcurrents. You can measure temperature at different points on the Earth's surface. And from that, you can get even better meteorological measurements at the micro level. Right now, that's not available. And so you can make some really good predictions. You're absolutely right. Sorry, I misunderstood your question.
Good evening, sir.
This would be the last question.
Can I ask one as well afterwards?
Good evening, sir. Good evening, Rahul, sir. Sir, I'm a student from Cluster Innovation Center, University of Delhi. Sir, I would like to ask two questions. First, according to you, what time would it take for a economically feasible product, such a product, to come in the market? Secondly, while traveling in its trajectory, if the copter makes a few flips and it loses its coordinates, how will the other network, shortly will the other network get updated of it so that the network does not crashes?
The first question is about, again, about products, right? And it really depends on what you're trying to do, who is interested in this technology. So this has only been out for about a year or so, and there's lots of interest in it, and depending on who decides to invest in it and what the applications are, the cost will be determined by that. The one thing I didn't talk about is the educational market. I think aerial robots really have the potential to get more and more kids interested in science, technology, and so on. Earlier we were talking about the big challenge I see is the brain drain, not in the conventional sense from east to west or west to east, but from the technology fields to the non-technology fields. And I think by having platforms like this, you really get high school children addicted to technology. So I really see that as a way of pushing this forward.
About the question regarding the coordinates, if the coordinates are lost.
Right. So if robots get lost all the time, and this is the same kind of thing that tells a cell phone network that a cell phone user has disappeared, right? And because these robots are constantly pinging each other and talking to each other, so the absence of a ping means somebody has sort of left the network. And that's pretty easy to detect.
Good evening, sir. My name is Deepak. I'm from Andhra Pradesh. So India is an upcoming country. It depends only on agriculture. Most of the part depends on agriculture. Is it going to be helpful for farmers of India in any way?
Is it going to be helpful? Sorry.
For farmers of India in any way, sir, for agriculture purpose.
Or is it going to help farmers? So we talked a little bit about applications to agriculture, and I think the technology will eventually change the way we think about agriculture. It has to, because of the pressures on farming.
Mr. Gandhi.
Yeah, I have two questions. The first one is a layman's question. When does a machine actually become a robot? And the second question, what about this technology concerns you? What worries you about this technology?
Let's see. When does a machine become a robot? So if you go back, well, the word robot is abused, and anything that performs things automatically is called a robot. But when we think about robots, we ascribe to it an almost human-like intelligence, the ability to look at the information and then take actions based on the information. And these days we've also come to expect some amount of learning. the fact that if you do a task, 3 or 4 times, the 5th time around it's going to be better. And so this notion of being able to learn and being able to adapt. So these are things that I think separate a machine from a robot. Quite honestly, in the field of air robots, the thing that does worry me most is the fact that it's so easy for the bad guy, to use a technical term, to strap on a piece of explosive to one of these aircrafts and fly it into my house, right? So these are things we need to be worried about, and I think as we talked about earlier, it's important to be at the cutting edge of this technology so you know what the potential threats are, and you can actually start thinking about how to defend yourself against these threats.
The question and answer session now comes to an end. May I now request Professor Sudipto Mukherjee to kindly give us his brief reaction to Professor Vijay's presentation and to our discussions. Professor Mukherjee is one of India's leading roboticists, Professor of Design and Manufacturing at IIT Delhi. Professor Mukherjee has been an IIT faculty member for 20 years, 4 years at IIT Kanpur and 16 years at IIT Delhi. He obtained his BTech from IIT Kanpur in 1985, MTech from Ohio University in 1988, and his PhD also from Ohio University in 1992. He is the owner of 15 plus patents. He is part owner of a technology startup in the business of developing driving simulators. He is a winner of many distinguished prizes. Professor Mukherjee, may I request you to kindly give us your reaction?
I didn't want to talk too much about robotics because Vijay is around, and he is one of the great guys. We do a little bit here, so maybe in some other context. What I would like to talk about more is about what happens if you really want to deploy robots in India. We understand that we have great diversity. Some places we have a problem of obtaining running water, some places we have a problem with storing bulk water. We even have diverse operator skills, different skill sets. And we're always struggling with this man-machine trade-off, will we get unemployment? So solved in many ways. So you have solar plants in both China and US, Europe. China, they have decided they're going to manually clean them, free of dust. US and Europe are still struggling with automation. So there are solutions at both ends of it. So it's from the point when things are deployed, like Vijay has deployed swarms, they have to be adopted by society, by technologies, by manufacturing establishment, and then they proliferate. So there has to be a critical level of capability that the society has to acquire before we manage to deploy them. And so that remains a question. And the thing that is been sitting around is that, so there are 2 levels. There is automation, right, where you chuck out, 5,000, 10,000 pieces in a row. When you're doing robotics, you have to take problems case by case, and many of us don't stay on the same problem for very long. We work for 5 years, we move away to new areas. What we really need to think about is robotics as a technology more suited to the Indian environment than automation has been for, say, the West and Japan. So one of the issues which came up in conversation with Rahul Gandhi was, what about investments? Should we invest? So one thing even which I will tell you is that success is not guaranteed, right? And a lot of us, in the university environment are in here trying to understand what is the fundamental principle involved here and trying to overcome it. So once you invest, success is not guaranteed. But if you do invest, we will at least figure out those segments which do not work, which is very important for us. And then he did mention that there are these takeaways which we get from robotic systems which do not proliferate. There are other systems, other theories, there are basic control problems, there are logistic problem, mapping problems which get solved in the process. So even if swarms are not there in the future, we will stand to gain a lot from it, just in terms of sheer mathematics and technology. And there is this theme which has been bothering us, which I mentioned that he has grown up in a steel city, I have also grown up in a steel city. We grew up watching the smokestacks and saying that is where life is all about. I mean, there was nothing which we had around us which was as good as the systems which were there inside the factories. And the basic questions that comes is, so do we have an academic environment that induces creativity? I mean, do we need to push the individual? Do we need teamwork? And so you saw these developments. Nice, fantastic technology. Is it teamwork? How closely are the teams knit? Do you inherit stuff from the person who just finished his PhD? Or is that everything is going on together? And you just have a large core which is synergizing the whole process. And one of the issues is that progressively students take the easy way out instead of indulging in the real effort of thinking. And we definitely have a problem with inspiring them, and we can only do that by giving them these fantastic examples and toys to build upon, giving them better and better modules to put together. And then there's obvious questions. If you decide to do robotics, first thing we think is, let's put an institute together, which will specialize in robotics. Do we really need that? Or, we need a more diverse kind of institutions. So we had IITs in the system already for 60 years. We are making many more IITs. One question again, Rahul Gandhi asked me is, should they again become like the old ones? Or should we need open universities in which there's a lot of cross-fertilization of ideas, and you watch ants and you make swarms? So these are deep questions, and I guess over some period of time we'll get more opportunities to debate it, and then I guess every time Vijay comes back in December, we'll tap into him and try and sort out what we can do to enthuse and evolve these technologies in a humane and holistic way. And so I guess that's all I have for you tonight. And then, because that's it. Thank you. Thank you, Vijay. Thank you.
This most enlightening discussion this evening, may I request Mr. Gandhi to kindly present a memento to Professor Vijay Kumar as a token of our appreciation for delivering this lecture, and to Professor Mukherjee for kindly being a discussant. Thank you, Mr. Gandhi. Thank you, professors. Ladies and gentlemen, may I request you to extend a warm round of applause to our chair, our main speaker, and our discussant for a very enjoyable and informative discussion this evening. Ladies and gentlemen, thank you once again for the honor of your presence this evening. And on behalf of RGICS, I wish you a very good night.